Good day, I'm Norman Wildberger. Today we want to go really far out in this remarkable successor limit hierarchy that we have outlined in our last few videos. So basically what we're doing is we're creating bigger and bigger arithmetic by thinking about sequence of operations, extending addition and then multiplication and then exponentiation and then this triangle operation that we've used quite a lot, the square operation and so on. We want to extend this list of operations in a rather interesting way, basically relying on two ingredients: the idea of the successor of an operation and the idea of having a limit of a given sequence of operations. So if we have a suitable sequence of operators or operations, say cross 1, cross 2, cross 3, then we can concoct this limiting sequence. So with these two different ways of extending further, we want to now explore the possibilities. And one kind of underlying question here is, how do we actually get our heads around what precisely a suitable sequence is? There's a bit of an open-ended aspect here that we want to explore. So we're going to try to pin things down, but I'm not going to pretend that I have a fully blown, completely laid out theory here. In fact, one of the interesting aspects of this whole story is that it may not be possible to lay out from the beginning what we're going to do. It may be more like you proceed in a certain direction, and then once you get to a certain level, you have to start making new decisions. And the new decisions that you have to make aren't, at least initially, apparent from where you began with. So it's kind of the zigzagging element that really requires you to think in a novel way, continuously or sequentially as you proceed. Alright, so I do hope that you've had a look at the previous videos, because if you haven't, this isn't going to make a lot of sense. So make sure you've watched the last few videos. And there we've created some kind of hierarchy, starting with these relatively simple operations that we're familiar with, and then proceeding on. Okay, so we started with the operation of addition, and then these first star operations of multiplication, exponentiation, and the triangle operation. Star 1, star 2, star 3. And that generated our first limit operation, which we called star infinity, and then we shortly changed the name to star n. Then we take the successor of star n to get star n plus 1, the successor star n plus 2, the successor star n plus 3, and then here we have a new triple of successors, and we can take the limit of the sequence that's starting with these to create star 2n. Then we can take some more successors, create star 3n, and then we have the situation where we have a new kind of pattern formed by this first limit operation star n, the second limit operation star 2n, the third limit operation star 3n, and that forms then a new sequence which has a new kind of limit which we'll call star n squared, which has then a successor star n squared plus 1, another successor, and then these three then generate a new limiting sequence, much as these ones did, called star n squared plus n. Okay, so we can keep going in a certain way, but at this point we want to become a little bit more efficient. So we want to, first of all, dispense with actually writing down the stars all the time. It's really only the subscripts that matter. So we can rewrite this thing without any stars, just the subscripts. So 0, 1, 2, 3, and then n plus 1, n plus 2, n plus 3, then 2n, 2n plus 1, 2n plus 2, 2n plus 3, 3n, and then jump to n squared. And then n squared plus 1, n squared plus 2, n squared plus 3, and that limit n squared plus n. Okay, this is described in the Math Foundations 181 on the fourth slide. There you see a rather big picture. Okay, so now to be a little bit more efficient and also descriptive about what's going on, so to understand more deeply what is involved here, we're going to make some more simplifications. We're going to start to replace these successors with just dots. After all, it's very predictable. Once you have star n squared, then the next one is going to be the successor, which will just obtained by adding the 1 to the label. So from n squared, we know the successor is n squared plus 1, and the successor of that is n squared plus 2, and the successor of that is n squared plus 3. So we can have a short form by replacing the successors just with dots. All right? So we can start with 0, which represents addition, and then this little dot here could represent the successor of 0, which is multiplication. The next dot, the successor of multiplication, which is exponentiation. The next dot, which is the triangle operation. All right, and then these 3 dots generate the sequence whose first limit is n. So what we're going to do is kind of disregard or sort of suppress the successors themselves, because they're sort of simple, and we're going to sort of focus on the first limits that we see. So there's a limit n, and then there's a limit 2n, and then 3n, and then n squared, and then so on. And something else that we're going to do is we're going to record the level of the limits. So this kind of limit here of n squared was different from the other kinds of limits because it was a limit of limits. It's a kind of level 2 limit. And so we might record that by putting a 2 underneath the arrow. Okay? So implicitly, these ordinary arrows should have 1s underneath them, corresponding to the fact that these are level 1 limits. And this thing is a level 2 limit, so it gets a red 2 underneath it. Okay, so with these conventions, we can now have another look at this successor limit hierarchy, at least up to how far we've gotten so far, and see it perhaps in a slightly new light. All right, so have a look at this. This is our successor limit hierarchy, at least up to a certain point, and where we've been very efficient in just having successors represented by single dots. Okay, so let's have a look at sort of how things go. So we start with 0, and then our first limit is n. And then our next limit is 2n, next limit is 3n. These are all level 1 limits. And then these 3 level 1 limits generate a new sequence which gives us a level 2 limit, n squared. Then we have some more level 1 limits, and they generate then another level 2 limit. Then another level 1 limit, a few of them. These 3 then generate another level 2 limit. And now we're in the situation of having 3 level 2 limits. They themselves form now a new identifiable sequence, and we can take their limit. So the limit of n squared, 2n squared, and 3n squared is n times n squared, or n cubed. And that's a level 3 limit because it's the limit of 3 level 2s. And now we have something that goes up again, because we now have a sequence with a 1 level limit, a 2 level limit, and there's our first 3 level limit. That generates a new kind of sequence which has a level n limit, namely n to the n. Okay, and now we kind of go back to the way things were. Very exciting, get a level n limit. And now we're going to go back down to ordinary successors with a level 1 limit, and another level 1 limit, n to the n plus 2n. And then our next 2 level limit, n to the n plus n squared, much the same as here. In fact, what's going to happen here now is going to be sort of a repeat of what has happened previously. After this level 2 one, then we get a level 1, another level 1, another level 1, and then another level 2, and eventually another level 2, and then these 3 level 2s generate a level 3, which is n to the n plus n cubed. That's a lot like this one. Okay. And then, well, then we have the same kind of situation as we had previously. We had an original level 1, and a level 2, and a level 3, and that gives us a level n, which is going to be 2n to the n. So from here to here is very much like from here to here. And then in fact the same kind of thing will repeat itself. That same stretch will be repeated from this end to the next end, which is down here. That'll be 3n to the n. So from here we'll have a level 1, a couple of them, and then a level 2, a couple of level 1s and a level 2, a couple of level 1s and a level 2, and once we have 3 level 2s, 1, 1, and 1, then we get a level 3. And then once we have a level 1 and a level 2 and a level 3, we get a level n by generating that sequence, and that'll give us 3n to the n. And now we're at the situation where we now have 3 level n's. Okay, there was that first level n, that second level n, the third level n. So now that's a suitable sequence which we can take a limit of, giving us something that we haven't gotten before, a level n plus 1 limit, namely n to the n plus 1. Okay, so some things to notice. First of all, let's say we have a level 3 limit. That's really telling us that what we're generating here is something with an n cubed. Okay? So the level here sort of corresponds to the exponent of the n that we're adding to what we had before. So here's an n plus 1 in red, that's the level, and not surprisingly what we get is n to the n plus 1. So the level is reflected in the exponent here. Another thing that we start to see is that the red indices themselves are doing something which is not so much different from what the black sequence itself was doing, except much more slowly. Okay. So you can think of the successors, if you like, as being almost like level 0 limits. We haven't said that, but you can think about it that way. So we have level 0 limits, and then we have level 1 limits, and then we have level 2 limits, and then eventually we get from that a level n limit. That's occurring right here. That's our first level n limit. In some sense, that's a reflection in the red arena of exactly this first initial sequence in the black arena. And here's 1, 2, 3 with limit n. That's somehow being reflected in having 1s and then 2s and then 3s and having limit n. And then what happens is again a kind of repeat of what we've had before. So there's a kind of a self-similarity that starts to appear here, that the sequence of red numbers, which records the level of the limit, starts to look a lot like the original sequence. So at this stage here, we've gotten up to n plus 1. So that's just up to there, right? We've made the transition. We've gone, in terms of the red labels, we've gone all the way up here, and now we're at that stage there. So we're going to expect that as we keep going, the red labels themselves are going to start navigating through the same table. There's a kind of self-similarity here, like a fractal aspect or something like that. All right, so this entire game that we're playing here is not meant to be viewed as rock-solid mathematics. I'm not claiming that what I'm doing is completely cut and dried in terms of the rules. Okay, but let's have a look at sort of what the rules are. And this is kind of experimental mathematics. I think maybe in the future this will be a bona fide sort of branch of mathematics. In fact, I really think it's a very rich direction, but very abstract. And it has a lot to offer. But nevertheless, we're in a process of sort of, trying to investigate it here, and there's nothing really, anything too set in stone at this stage. So far, the rules are something like this, that after 3 successors, we can create a limit. That's sort of our initial thing. We can create successors at any stage, and if we have 3 successors in a row, then we can create their limit. And that's a level 1 limit. And after 3 level 1 limits, we can create a level 2 limit. So we create a sequence from those 3 level 1 limits and what they imply. I mean, they really are just the starting points of a sequence. And it's that sequence that they're the starting point of that we use to generate the level 2 limit. Okay, and more generally, After 3 level t limits, we can create a level t prime limit, where t prime is the successor of t. So this happens not just at 1 to 2 and 2 to 3, but at more advanced levels as well. In other words, if we have 3 level n limits, then they generate a level n plus 1, which is the successor of n limit. And another thing that we've sort of observed is that, let's say that we have labels, and I'm just using t's here to be rather open-ended about what these labels actually are. So if t1, t2, and t3 going to tn is a valid limit, then from the most recent t1, t2, t3 level limits, we can create a level tn limit. Okay, what do I mean by most recent? Well, so what happens is that the limits go up and down, okay, and eventually you get a big limit. And after you get a big limit, then it's almost like erasing the table. You have to start again from the bottom, and you have to build up until you get something which is comparable to that previous peak. And then if you get enough of those peaks, then you can create something higher. So that's the general kind of thing, is that after you have something big, then you have to start with the small, sort of erases the previous ones from visibility. Okay, so that's what I mean by the most recent T1, T2, T3 levels. So it means that the labeling or limiting relation that are satisfied by the red ones reflect the limiting relations satisfied by the original black ones. So for example, n plus 1, n plus 2, n plus 3 has limit 2n. Okay, that's sort of at the black level. And that means that the first n plus 1 limit, followed by the first n plus 2 limit, followed by the first n plus 3 limit, will generate a suitable sequence which has a level 2n limit. And I remark, as I did before, that a successor can be viewed as a level 0 limit, sort of so that it all sort of hangs together, roughly. All right, so I want to zoom out now. Okay, I want to see a little bit less detail and a bit more of the big picture. So we're going to do that by disregarding detail. And let's do that by introducing these 2 green dots to mean that there's sort of lower level stuff in there that we are disregarding. Okay, so this is kind of a bird's eye view now, where we're not just ignoring the ordinary successors, but ignoring a lot of the lower level limits, especially as we get into the bigger ranges. Okay, we'll start with the sort of beginning. So we start with 0, and then 1, 2, and 3. And these things have level 1 limit, namely n. Okay, that's our first limit. And then eventually we get, after a couple of successors, we get 2n and then 3n. And then there's a level 2 limit, which is n squared. Okay, and then there's some stuff which is basically like a repeat of what we already have. Okay, and that's actually another interesting aspect of this thing, that once you have a sequence, then it tends to repeat itself. You can replicate it. So if you have a kind of a copy button, you just copy that sequence, and that sort of slots into here. So going from n squared, there's some stuff, to another level 2 limit, which is 2n squared. And then, in fact, a similar kind of range of stuff, which then generates the next level 2 limit, which is 3n squared. And then it was these 3 level 2 limits that generated our level 3 limit, n cubed. Okay, and then we had a level 1 limit here, a level 2 limit here, a level 3 limit here. Those are labels which themselves have a limit, because we can see 1, 2, 3 has limit n. And so the first 1 and the first 2 and the first 3 are legitimate entities to create a new sequence, which is going to have limit of level type n. And there it is there. It's n to the n. It's a level n limit. All right, and now we could essentially take everything that we have up till now and copy and paste it, and so stick it in here, and eventually we'll create another level n limit, giving us 2n to the n. The same copy and paste right in there, giving us another string with ending in this level n limit and 3n to the n. And now we have 3 successive level n's. Okay, 3 successive level n's gives us the successor of that one, which is n plus 1. There's our first n plus 1, which is n to the n plus 1. Okay, now we copy everything that we have here, at least copy the steps, right, and basically paste it in there, and we get a whole sequence much like this, and we get our next n plus 1 limit, which is 2n to the n plus 1. And then copy it again right there, and we get the next n plus 1, which is 3n to the n plus 1. Now we have 3 successive n plus 1s. That generates an n plus 2 limit. Okay, more stuff to the next n plus 2, more stuff to the next n plus 2, which generates the next n plus 3 limit. There's n to the n plus 3. And now the first n plus 1, first n plus 2, the first n plus 3, that corresponds to these 3 dots here. That sequence has limit 2n. So this one, and this one generate a new sequence, which is going to have level limit 2n. And it is n to the 2n. The exponent here is pretty well always the level of the limit. Okay, and now we're going to skip some more stuff. I mean, you can kind of imagine how things go. In fact, you could actually, fill in a lot of the details to try to give some more structure to what we're doing here. So from this 2n, eventually we get to a 3n level limit, which is n to the 3n. And now once we have an n, the last n was this one here. We have n level limit, and then a 2n level limit, and then a 3n level limit. Let's look at that. So we have n to the n, and then n to the 2n, and then n to the 3n. And they generate for us a level n squared limit, which is n to the n squared. Okay, that's pretty cool. And then there's lots of other stuff. And eventually, so, I mean, we've got just an n squared. So in terms of the labels, we're over here. The labels in red are only at this stage here. So we're quite far ahead of the labels. So eventually we keep on going, and eventually the labels would get up to n cubed, which is right here. Okay. So once we get levels n cubed in terms of the labels, then we know that the n squared, and the n cubed generate an n label. So correspondingly, the corresponding things here are going to generate an n to the n limit, which is n to the n to the n. Okay, now let us stare at this for a second, and let us note that now we've just created this n to the n level limit. N to the n is where on our picture? There it is there. Okay, we have an n, and we have an n to the n, and now we have an n to the n to the n. Right? So think about the sequence here with this n, and this n to the n, and this n to the n. All right. So this is a level 1 limit, this is a level n limit, this is level n to the n limit. That is also a reasonable sequence. That's also a reasonable sequence, which has what kind of limit? Well, we could write it like this: n to the n all the way up to the n, where there are n of them here. It's a different kind of limit. It's also obtained by a very valid sequence of limits that we've already obtained. Level 1, level n to the n. But we have to kind of go a little bit beyond what we were doing up till now and have to think a little bit bigger. Say, okay, we can think bigger. We can go up a level. Of course, we've been going up already. We've been going up at this incline, but now we want to go up at even a steeper incline than we were before. So we can always do this, I claim, at least, until we start running out of room in the universe or something. But we can do this. We can always look for a more steep path than the one that we're currently on, especially in this game. So now we are creating this new kind of object, which of course we recognize, right? This is actually n triangle n. We've got an n triangle n in this picture, or if we like, n star 3n. And what kind of a limit is this? What should we put here in red? Well, that's a good question. I think it's almost a limit of the same kind, really. It might be that we should put something like that there as well. Maybe one could argue about this, what kind of a limit that is, but in any case, it's the situation now that this limit that we're doing here is, I think, pretty comparable to the object itself. So we get a situation where the limit and the label have pretty well caught up. Okay, up till now, previously the labels were lagging far behind the actual objects, but at some point they have this potential for catching up. And for those of you who have studied ordinal arithmetic, you will probably say, oh, this is all very familiar to us, so no doubt you can tell us more clearly what's going on. But you see that there's a distinction here, right? We're still basically talking, at least in principle, of finite integer arithmetic here, natural number arithmetic. All right? There's no infinite sets at all here. So this is a kind of mirror to what the set theorists are doing, but in a more finite domain, even though the actual domain is, actually incredibly big. In principle, you couldn't really write down these operations effectively, in the known universe, even for very simple numbers. If you wanted to calculate, 5, then star this operation 6, well, it would easily blow out of the universe, I think, in any kind of reasonable way. So we've come quite a ways here in creating these bigger and bigger operations for natural numbers. Now, underneath this direction, there's actually some very interesting computing or programming challenges. And I want to alert the programmers amongst you of this very interesting possibility of thinking about things. So the challenge is to write programs that actually implement these various operations that we found in our hierarchy. So for example, we started out, our first limit was star 1, star 2, star 3, etc. That sequence generated this limit star n. And so to get at star n, we really had to use this basic defining property, right? The defining property was that m star n k, if m and k are natural numbers that we want to multiply using this operation, then the definition is that it's m star kk. And so to implement this, you have to have a program that allows you to compute all of the stars. You really need to have all of the stars at your disposal. And we could say that in the following way, that we really need a program that computes for natural numbers m, k, and let's say p, the product m star pk. Right? We want to be able to do that kind of general computation. And if we can do that general computation, well, then calculating m star n k will be easy. Now this particular combination of things is actually something with a very long and distinguished pedigree. It's essentially what's called Ackermann's function. Okay, it's not exactly Ackermann's function. Ackermann's function differs from this by just a bit of a shift by one in a couple of these variables. Okay, but it's essentially the idea of Ackermann's function. And that goes back quite a long ways to 1928, long before we had computers and such. All right, so this is a very concrete example of a challenge to actually write down a program that will input three natural numbers m, k, and p and calculate this thing here. And that's not that hard. People have done that, but that's probably a good starting point. So if we consider going up a few rungs, say to the limit star n, star 2n, star 3n, going towards star n squared. All right. So in order to get this star n squared operation, we then really want to have all of the star kn's. We have to have this entire sequence at our disposal. Because the definition, I remind you, of m star n squared k, m and k are natural numbers, the definition is that it's m star kn k. We take the kth element in this sequence and use that as the operation. Okay, so to implement this kind of thing, you'd want to have a program that computes something like this. That computes for three natural numbers, say m, k, and l, the product m star ln k. So when l is 3, it would calculate m star 3n k. So we want, though, to have control over not just any one of these, but all of them together. All right. So we encode that by a bigger program that inputs three things rather than just two things. Now, if you are able to write such a program, and it's, I think, a pretty good challenge, then, of course, running it actually, except on the most trivial of numbers, will be something that's problematic. Well, you can press the run button, but what will happen is that this thing will just start churning away and start filling up your hard drive, and eventually everything will just overwhelm your system. So you're not going to be able to run this and finish the program generally, but nevertheless you can still create such a program, and this program then is a tangible manifestation of this operation, even if we can't actually implement it by running it to conclusion. So I think there's an interesting challenge here to those who like to program, which is quite a lot of people these days. So who can create a program for, say, star n squared? And then going up some levels to star n to the n, for example. Yeah, this is already perhaps hugely challenging. And maybe even ultimately for something like star n triangle n. I imagine these are very challenging. You probably want to start much more modestly here, and but it's something that people can actually write down programs, and we can check whether these programs actually work theoretically. I think it's cool. Okay, so what happens after this star n triangle n that we've now arrived at? Of course, we can keep going. We can always take successors, and then having a few successors, we can take limits and so on. So we can keep on going, but I don't really have a very clear idea of how the story unfolds. And I have some intuition, and it's, I think, rather challenging to proceed up this ever increasingly sloping path. So it's a very steep road, and there's all kinds of forks, and you have to make decisions. And there's probably pitfalls and wrong turns possible. So, one gets very high with, of course, very heady scenery and dizzying heights. So, just to give you an orientation, we could start, of course, with star n triangle n, and we could do kind of obvious things. We could take successors. Okay, we could take, add 1. Maybe we'll just replace this with the index itself. So we'll just start with n triangle n. So after that, we could, of course, add 1, and then we could add 2, we could add 3, and so on. Eventually, we would add n. Okay, and then eventually, without being very consistent here, we'd get something like n triangle n plus, now the second thing here can really go through the entire sequence that we've already generated. Right? We can go to n squared, to n cubed, to n to the n, and so on. So eventually we get to essentially this thing itself again, repeated here. And that we wouldn't call it this, we would call it 2n triangle n. All right, so it's a long road, though, from n triangle n to this one. Basically, you have to go through the entire procedure that we've already gone through. And then after this, we'll eventually get to n times n triangle n. And let's think about what that involves. So that's like n times the sequence, n to the n all the way up to the n, where there's n of them here. All right, that's n triangle n. And when we multiply that by n, what we're doing is we're basically adding 1 to the exponent. So we could write that as n to the, okay, then there's all these n to the n's, and so this part of it is having 1 added. Okay, then one can keep on going, perhaps in some way, and eventually this 1 then can become an n, and then we can play kind of the same game that we're doing at the previous level, and this can eventually become, say, multiplying this whole thing by n instead of just adding. And then that effect is really actually to add 1 to the next little tower. Okay, and so there's a possibility of eventually, adjusting each one of these exponents of, increasing that top n. So there's all kinds of things that possibly could happen here. And the natural question is there some consistent way, perhaps, of getting to, and now it's questionable here, okay, so one has to think about these things. Does it make sense to perhaps eventually finally get to something like n star, well, this was n star 3. How about n star 4n? This is n triangle 3n. Is it possible to create some sequence of sequences of sequences of sequences and so on? So eventually we get n triangle 4n. Well, if we are able to do that, and if we have then n triangle 1, n triangle 2, n triangle 3, can we sort of program it so that we can get an arbitrary one there? So if we're able to get the arbitrary one there, in other words, if we're able to extend our thinking so that we might be able to get this, then we could take the limit of that kind of sequence and we could end up with n star n n. And now possibilities emerge that now this label down here can start being subjected to the same kinds of ladder considerations that we've already been talking about. Maybe it might be possible to eventually get to something like n star, and then this label down here is n squared n, or maybe even n star n to the n. And of course, all of these things here are just meant to be the labels of the original operation. So these are already labels of our operation star. Okay, this is all very questionable. It's all very murky. To me, it's like a fog out there. I don't really know how it goes. I can't say that there's a consistent theory here. But there's probably all kinds of exploration that can be done here. Okay, I think teams of people could work on this for decades, really. It's just some endless zoo. Or maybe it's not an endless zoo, but maybe it's some vast labyrinth. Maybe it's a long and winding road. Okay, but to be really explicit, what we want is ultimately to have control over these things in the sense of actually having computer programs. Okay, so it would be fun to have computer programs that actually sort of follow our theoretical constructions, and that's a sort of way of pinning down what we're doing so that we're maybe not so much in fantasy land. We certainly run the risk of emerging to some kind of fantasy journey here. Okay, so lots of fun, I think. Lots of thinking, perhaps, for future generations, and perhaps set theorists who are maybe tired of doing the old ordinal stuff, which is a little bit shaky and dubious, might want to come and have a go. They could probably help us out here. Okay, so that's all very good. We've gotten a good appreciation for the complexity, the overwhelming scale of dealing with arithmetic at higher and higher levels. What we would like to do now is, armed with this appreciation, maybe almost a sense of humility, is to go back to the fundamentals of arithmetic and now have another look at really what basic arithmetic is actually all about. Arithmetic with natural numbers. Given what we know now, how are we actually going to set things up in a way that's mindful of the differences between working with smallish numbers, medium-sized numbers, very huge numbers given by mathematical expressions, but perhaps not actually supported by concrete arithmetic. So there's distinctions to be made, and there's, I think, a very rich landscape of even basic arithmetic with natural numbers that we really have to grapple with. It's actually a fundamental, basic building block of mathematics, of course. So we do need to think more carefully about that. In the next video, we're going to start doing that. So back to very basic arithmetic. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.